Today's topic is performance efficiency in cloud systems design. Subscribe to the channel and like this video. Much appreciated. Performance efficiency is one of the pillars in every major well-architected framework. AWS, Azure, and Google Cloud all name it. All three define it the same way. It means using computing resources efficiently to meet your requirements and staying efficient as demand and technology change. Fast is not the goal on its own. You can buy speed by over-provisioning until the bill hurts. Efficient means fast for the resources consumed. That is speed you can afford to keep. So state a target first, then reach it with the smallest sensible amount of infrastructure. Performance is a feature your users judge before they judge anything else. Retail and search teams have repeatedly tied added page latency to lost conversion and reduced engagement. For a simple application, the work is small: caching a query result or putting static files behind a content delivery network. At scale, the same pillar turns into architecture because analytics workloads process far more data than any single machine holds. Why does this matter so much? Understanding this also protects you from the most expensive mistake in cloud design. That mistake is buying a bigger instance to hide an inefficient algorithm or a missing database index. Two numbers describe almost every performance conversation, and confusing them causes bad designs. Latency is how long one request takes. Throughput is how many requests you complete per second. Improving one can easily hurt the other, since batching work raises throughput and latency together. Measure latency at percentiles rather than averages. An average hides the slow tail users actually notice. The P99 figure means the slowest 1% of requests. That 1% includes your most active customers. Decide which number your workload is judged on before you tune anything. An interactive API is a latency system. A nightly analytics pipeline is a throughput system. Caching is the highest leverage technique in this pillar because the fastest work is work you skip. In-process caching is fastest and least consistent since every instance holds its own copy. A distributed cache gives every instance one shared view. Amazon Elasticache, Azure Cache for Redis, or Google Cloud Memory Store. That layer commonly turns a 30-millisecond database query into a sub-millisecond lookup. A content delivery network pushes cached content to edge locations near your users. That is caching and data locality together. Why does proximity matter? A request crossing an ocean pays around 100 milliseconds that no code change can recover. Every cache needs an invalidation plan. Stale data is the price you pay for speed. Scaling comes in two directions, and cloud design strongly favors one of them. Vertical scaling means a bigger machine, it needs no code changes, and eventually hits a ceiling. Horizontal scaling means more machines. It has no practical ceiling, but requires a stateless application. Stateless means any instance can serve any request, so session data lives in a cache rather than local memory. Auto-scaling makes that elastic, adding capacity when a metric crosses a threshold and removing it when demand falls. Scale on the signal that reflects real load, which is often queue depth rather than CPU. A load balancer sits in front. It spreads traffic across the fleet and removes failed instances from rotation. Watch your scaling lag, because an instance taking 4 minutes to boot cannot answer a 30-second spike. Resource selection is where large performance wins hide, and it costs nothing but attention. Cloud providers offer instance families tuned for compute, memory, storage throughput, and graphics processing. Running a memory-bound cache on a compute-optimized instance wastes money and performs worse than the correct family. Serverless changes the calculation again, because AWS Lambda and Google Cloud run scale to demand with no fleet to manage. They suit spiky and event-driven work. Cold starts add startup latency you must design around. The frameworks call the broader habit democratizing advanced technologies, which means letting the provider run the hard parts. A managed search or data warehouse service embeds performance engineering you would otherwise build yourself. Most slow applications are not slow at the application tier. They are waiting on data. Check indexing first, because a missing index turns a lookup into a full table scan. That gap grows with your data. A query fine at 10,000 rows collapses at 10 million. Read the query execution plan rather than guessing, since every major database reports what it chose to do. Read replicas move reporting and read heavy traffic off the primary, though they lag slightly. Route anything requiring immediate consistency back to the primary. What do teams forget most often? Connection pooling is the quiet fix teams forget, because opening a connection is expensive and slots are limited. A pooler like Amazon RDS Proxy or PG Bouncer keeps warm connections. It stops a scaling event from exhausting the database. Learn more at systemsarchitect.io. Like and subscribe to the channel and follow the playlist. Not every task needs to finish before you answer the user. Asynchronous processing takes slow work out of the request and hands it to a queue or an event stream. The user gets an immediate acknowledgement while resizing or emailing happens behind the scenes. Amazon SQS, Azure Service Bus, and Google PubSub also absorb spikes that would overwhelm your workers. Event-driven architecture generalizes this, letting components react to events instead of blocking on each other. That decoupling means a slow downstream service degrades one feature rather than every request. Shrinking what you send matters just as much, so enable compression on responses. gzip or Brotli commonly cuts text and JSON payloads by roughly 70%. That directly reduces transfer time on mobile networks. You cannot optimize what you do not measure, so observability comes before tuning. Collect metrics for latency percentiles, throughput, error rates, and saturation across every tier. Distributed tracing shows where a single request actually spent its time. Use AWS X-Ray, Azure Monitor, or OpenTelemetry. The slow component is frequently not the one you suspected. Load testing then tells you how the system behaves before your users do. Establish a baseline and run tests that mirror real traffic. Treat a regression against it as a failing build. All three frameworks treat this pillar as a continuous practice rather than a one-time project. New instance generations and managed services arrive constantly, so revisit your choices on a schedule. The direct return is user experience, since responsive systems keep people engaged and converting. Efficiency also lowers cost, because the same traffic served with fewer resources is a smaller bill every month. It improves reliability too. A system with performance headroom absorbs a spike instead of cascading into timeouts. Operationally, the observability you build for performance is the same observability you need during an incident. It grows your career as well, because engineers who can find and fix a bottleneck get trusted with the systems that matter. Performance is a trade-off, and there are places it should not win. Caching trades consistency for speed. Financial balances and inventory counts often need the authoritative read instead. Aggressive optimization also trades away simplicity, and a hand-tuned system your team cannot debug is a poor outcome. When is optimizing actually waste? Optimizing before you have measured is the classic waste, since most runtime lives in a small fraction of the code. Extreme low latency costs real money through over-provisioning, multi-region deployment, and premium storage. Ask what the business actually requires, because 200 milliseconds is fine for a search page and unacceptable for a trading engine. Performance efficiency means meeting your latency and throughput requirements with the smallest sensible amount of resources and staying efficient as demand and technology change. The core levers are caching at multiple layers, scaling horizontally behind a load balancer, and choosing the right resource types and managed services. Fix the data tier with indexes and pooling, and move slow work off the request path. Measure with percentiles and tracing, and validate against a load-tested baseline. Revisit the design regularly, because performance efficiency is a continuous practice rather than a finished task. Thanks for watching and listening to this, and subscribe to the channel. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.